Hello. Hi guys, good morning. Welcome back to new video. Ki hal chal? I hope you guys are doing good. In this week on this problem, shortest subarray with sum at least k. Now, if we look at the problem, it simply says that we are given an integer array nums and an integer k. As you can see, nums and an integer k. We have to return the length of the shortest non-empty. Obviously, if I take empty subarray, that will be obviously shortest, which is null, no element. But he is saying take the length of the shortest non-empty, which means having some elements of nums, such that the sum of that specific subarray which you have taken is at least k. If there is no such a subarray, then my answer is -1. You know obviously what a subarray is. It is continuous elements. Now, very basically, if you had done similar problems or you had been working with us, as in like understanding with us, so you simply can feel that I want a subarray, I want to shrink its length. What I can try to do is I can keep a window logic, which means I will take the corresponding array. I have the element 2. Okay, it is less, increase the window. Now the sum is 3. I want the sum as 4. Again, increase the window. Oh, now the sum is 4. I am good to go. So I will say the current answer is 3. But I want to minimize my answer. So I will shift my left window. Oh, now the sum has become 2. Oh, it is less. So now start increasing the window. Now the sum has become 5. Oh, it's great. So, but yeah, answer is still a 3. Then start to minimize the window. Minimize the window. Oh, the window has become, like the sum has become 4 and the window has become 2 of length 2. So answer is minimized to 2. Try again minimizing the window. Oh, L, it has become 3, but I wanted 4. So I should not. I should increase my R. Now it has reached N. I'm good to go. So you can simply feel that, okay, I can apply a sliding window logic. If you don't feel it, I should have recommended you, please go and watch your 2-pointer crash course. In that, we have ultimately told how you can think and feel for it. But if you have felt for sliding window, then you might have a question. Aryan, why not you can apply the same? If you would have watched the crash course, you would have known why, when and when not you can apply 2-pointer, as in this kind of a logic. In this case, I was able to apply it because as I keep on increasing or as I keep on going right, my sum increases. As I go left, my sum decreases. So as I increase my window size, my effect is linear. Okay, it increases. As I shrink my window size, my sum decreases. Effect is also linear. But the constraint says the values are negative also. In case of negative, if I go and put my step forward, which means if I expand my window, here the sum decreased from 2 to 1. If I again expand, it again increased. So on expanding or shrinking the window, the behavior is not certain. In this scenario, again, we have taught this in our crash course, so no worries. It's a very small crash course. You can just simply go and watch it so that you understand the basics of 2-pointer. So we realize that obviously we cannot apply 2-pointers, or you can say sliding window logic here itself. But can you apply in other problems? Obviously you can. If you look at this problem, it is exactly same. In this, you can apply 2-pointers approach, which is the same approach which I discussed before, because the values are positive. Now you realize, okay, you cannot apply this logic. Then what you can do? How you can solve it? Now, a simple, very basic brute force approach simply says that Aryan, take all these subarrays, get the sum of that specific subarray, which will take O of n time, and compare it with k. If it is more than equal to k, if yes, then increase the count by 1 or decrease your minimum answer, which is length, by the corresponding value. It will be O of n cube. But these standard basic brute force approach, we have already seen the basic optimizations here is that rather than computing a subarray first and then finding their corresponding sum, do it parallelly, which means find the subarray and also parallelly keep on computing the sum. If you don't know how it is done, it is simply done. Okay, if I am at I here, I know the sum so far is 2. If I put my j here, my sum become 2 minus 1, which is 1. If I put my j here, so my sum become 1 plus 3, which is 5. So just by going on to j, I keep on adding the current value of nums of j in my previous sum. I don't compute the sum altogether. So this is how I can approach or get it in O of n square and compare it in O of 1 time. Still O of n square will be the complexity, which will still give you TLE. But there is one more better approach which you could have taken, which is that you take all these subarrays, okay, O of n square, compute the sum of a specific subarray. Rather than taking O of n time, you can do it in O of 1 time by doing some pre-computation by prefix sum technique. If you don't know prefix sum technique, just go and write on YouTube prefix sum by Aryan. In fact, you will get the video. But I'll give a quick glimpse. What it simply says is that by some pre-computation, I will show you what the pre-computation is. But because of that pre-computation, you can achieve any range sum in O of 1 time. What I mean by that, if I have this array 2, -1, 3 and 3. I have the corresponding prefix sum as 0 plus 2, 2 plus, again, I am taking sum of the previous value, -1, 1 plus 3, 4, 4 plus 3, 7. Now, when I have computed this prefix sum, now if I ask you, what is the subarray sum in the range 1 to 2? Although it is just 2 elements, but still, even if I would have asked any bigger range, answer will still can be computed in O of 1 time. How? If I ask you this, which means I to j, so the answer will be prefix sum of j, which is 4, minus prefix sum of I minus 1, which is 2. So 4 minus 2 will actually give you the range sum between 1 and 2. How you did it? I to j, if I am going to ask you what is the range sum, you will say prefix sum of j minus prefix sum of I minus 1. And there is no hard and fast rocket science here. It is simply, as you can see, that up till you want the sum up till this point, which means this is included here, this is included here, so you don't want to include anything here. So this entire range sum, you are subtracting from this entire range sum, you will get simply this range sum. That's it. So now you realize, okay, you could have also used prefix sums just so as to optimize your brute force approach. But still, it doesn't let you get to the answer of O of less than O of n square. How will you do that? See, Maqsad nahi bolna tha. Your main aim was getting the minimum length, and also how minimum length? Subarray sum should be more than equal to k. To compute the subarray sum, we realized we have a trick of doing a pre-computation by using prefix sums. But minimum length, I realized I cannot use a sliding window approach because things are not linearly increasing or decreasing. So what? So what to do? Now, because of that, which means now my ultimate maqsad remains that finding the minimum length. And so far the observation here goes that for any I to j, I know that the range sum will be prefix sum of j minus prefix sum of I minus 1. Which means I am trying to go towards a linear or linear log approach, which ultimately says that, okay, if I am at a corresponding j, so I know prefix sum of j. I also know the corresponding k. So as to get this value is my maqsad, that I should get this value. Now, you already know, again, I have replaced this with x, which is, let's say, I minus 1. But this x is nothing but any index before j, such that it is less than, like, it is very less. But why are you focused on very less in this approach? You just want something, right? My equality is not equal to, my equality is more than equal to k, which means this is fixed because I'm saying I'm iterating on every j, because obviously you will have to go to every element. This is fixed. You want that this condition should be satisfied so as to get you any result whatsoever. So I will try to get as minimum a prefix sum of x as possible, which has come before. So again, so as to get any result whatsoever, I will see how will I minimize my result, but so far I am concerned about any result I can get, and then I can approach getting the minimum result. So I realized, okay, I will get the as minimum value as possible from that left portion, which is left of j, and thus if that as minimum, because obviously I'm taking minimum possible prefix sum of x in the left side, if that also is not able to satisfy this condition, obviously no other element will be able to do that. So I can very easily move forward. So now, for so far, to get very small minimum, or I should say minimum or least value in some portion, what you can use as a data structure. Obviously, you can use a tree map, which is also called as a simple map in C++. You can use a tree set, which is also called as a set in C++, and you can use a priority queue, which is also a priority queue, or you can say a MinHeap to get the minimum element in O of log n time. So, but are you just storing minimum value? Obviously not, because minimum value will be used to put that value here, but ultimately your maqsad was to find the minimum length. Length is computed by indexes and not values. So minimum value, I will put it here, but I want minimum index also. So I want j and the corresponding index which gave that minimum value. So in that data structures, I should be storing the corresponding index also. So if I use a map, I can use a key as my prefix sum and the value as the index. If I use a set or a priority queue, I can make a pair of prefix sum, which means the value and the corresponding index. So far you realize, okay, you can use this specific data structures like prefix sum, priority queue, MinHeap, tree set, tree map to store or to get your minimum value. But Aryan, still it did not solve the fact that you wanted minimum length. Okay, you are getting one answer, but is that answer minimum? That's not the case in this example. Let's see how we get it. But so far we have got to some point. At least we are able to get some answer, not the minimum, but some answer. Okay, so let's try to iterate. Again, obviously I will have to iterate linearly once. So let's try to iterate. As I iterate linearly, let's see how I will handle it. Now you can easily see that I have prefix sum. In the prefix sum, you always have a 0 in the very beginning. You can handle it separately. What I mean by handle it separately, what I mean is that if I land on to 4, as you can see, I want to get a sum as 4. So 4 minus 0 is more than equal to 4. So either I can place this 4 also in my priority queue MinHeap, or what I can do is I can simply say, okay, if any prefix sum of j, if it is more than equal to my k, then obviously I assume that I can take entire array in this range from beginning to that index j. So this is I can handle it separately, and when I say handle it separately in my code, you will see that prefix sum of j, if it is more than equal to k, then I will simply minimize my answer, and this answer is nothing but the length itself by simply j plus 1. Aryan, why j plus 1? Because if I am at index j, number of element or the length will be nothing but j plus 1, which is 3 in this case. Index is 2, elements are 3 in this case. Okay, let's go on to the actual crux here. If I am at j, which means I know the prefix sum of j, I need to find the smallest value so that it is more than equal to, again, after subtraction, it is more than equal to my k. My MinHeap is empty. Okay, go on. Let's go on. Okay, now I am at this specific j. But now my MinHeap, now if you remembered, my MinHeap, as I go on to next element, I will put the current element in my MinHeap. Okay, now my MinHeap contains 2, 0. Now what I will do? Okay, I am at this j. I will say the current value is 1. My MinHeap minimum value is 2. 1 minus 2 is minus 1. Is it more than equal to k? Nah. What to do? Obviously, go on. Go on as in do what? Obviously, go on. Go on further. But before going on, put the current element in the MinHeap. And when I say current element, which means the corresponding value, which is this, and the index, which is this. Okay, let's go on. And again, this is a MinHeap, so you can see that 1, 1 will appear in the top. Now, I am at this value. Okay, the value is 4. And as I showed you, the corresponding thing that if the value is itself more than equal to k, you can simply minimize the answer. And also, if you want, you could also put 0, 0 in the corresponding MinHeap, or I should say 0, -1 in the MinHeap, and then still solve it. It's totally up to you. But as this step is done, I will also put 4, 2 in the MinHeap. Now I go on to next element, which is the value 7. Okay, 7, I will get out the minimum value. Minimum value is 1. Okay, 1. Is it more than equal to k? Yes, it is. Minimize your answer. Current answer so far, which you have grabbed from the earlier step, was a 3. But obviously minimize it, which means the current j, which is 3, and the top element here, simply grab it out. Okay, I grabbed it out. Index will be 1. Okay, then I got it as a value of 2. Oh, good. Minimum value. Simply minimize your answer. Obviously, this is now no more used. I can simply remove it. You might say, why to remove it? Won't it be used in future steps? Obviously not. Because if you use specific index I, specific index j, in future, let's say if you are using another index m, and then you are trying to use your I with that specific index m, obviously this distance is larger than this distance. So if any index once used will never be used in future. So that is the reason I can easily remove it. Now after removing, my array looks like this. Let's still try to minimize my length. How I will do it? 7. I will remove it. Value is 2. Value is 2. Is it more than equal to k? Yes, it is. My k was 4. So minimize the answer. Length. current answer length is 2 as I did in earlier step. Now it is 2 here. J is nothing but current index, which is 3. 3 minus 0, because current index is 0. Is it more than equal to, is it more? No, obviously not, because minimum was 2. So again, simply remove it. Now my element, again, let's say if I remove it, now my value became 4,2. Oh, obviously 7 minus 4. Is it more than equal to K? No. In that case, my answer still remained a 2. Okay, let's move on forward. So this is how I can simply do it. You saw what happened. You minimized your answer because you're always taking the minimum length and trying to see if that works, good. And because of the fact you are putting elements, as in adding elements and removing elements only once from the priority queue, you can simply say that operation of putting and getting is at max once, which means total twice operation on any element, and each operation is log n, so complexity will be O of n log n. And thus, by simply using a priority, you can simply solve it. Now, I made a simple pair. Now, pair simply here indicates two values, where the one thing is sum and other thing is index. Now, I simply went on and took a corresponding min heap. Prefix sum, again, this line indicates that I am sorting this by the corresponding value, and that to minimum value should come first. Then I iterated on all the indexes from j to like 0 to n, and then I found out that, oh, if the prefix sum is more than equal to k, then minimize the answer. This is the corresponding step I showed you, which was here in this case, right? Which is this specific case, when, okay, the value is itself more than equal to k. Although you can handle it in the min heap also by putting up a dummy value of 0, comma minus 1 as an index, so as to handle it, but also you can handle it separately. Now, here in this case, I checked, oh, if the heap is not empty and the current sum, which is prefix of j, minus the minimum element or minimum heap pair corresponding value, if after doing this operation of subtraction, if it is more than equal to k, I am good to minimize my length, as I showed you in last dry run which I did, which is this specific one. I am good to minimize my length. And when I say minimize my length, make sure to remove that specific element. Again, peak says just see it, pole says remove it. So if I am minimizing my length, I know this pair or this thing will never be used in future. So simply pole it, which means remove it also from the priority queue, and then keep on doing it until you can do it. Now, ultimately, make sure to put the current element also in the priority queue. So I will just put the current element offer, which means add. I can also replace by add. Add that in the priority queue. What I will put? I will put prefix sum and the corresponding index. And thus, ultimately, after trying for all the indexes, if my minimum answer is still int max, you were never able to achieve the corresponding minimum. So -1, else the answer is minimum. So you saw that the complexity will be O of n log n and space will be O of n because of you are using a corresponding new data structure, which is heap. Can you improvise it? When I say improvise it, obviously I'm trying to go towards a linear time complexity. Can you do it? Is the question. Obviously you can, but for that you have to look back and see what you did earlier. Let's recap what I did in the above approach of MinHeap. When I told you that I was at the corresponding index j, which is 3. I took a look at the minimum element. Okay, it was 1, 1. 1 is the value and this is the index. I saw it is more than equal to k. And then I simply tried to minimize my answer. But then when this was removed, I then took a look at next value, which is 2. Okay, it was also like 7 minus 2 was also more than equal to k, but the answer never increased. Why did the answer not increase is the question. The answer did not increase is because the smaller value having larger index, larger value having smaller index. What I mean by that is any larger value before a smaller value is useless. If I repeat that again, if I am at this specific index, this is index 1, value is 1. This is index 0, value is 2. For me as value 7, I was trying to look for a minimum value, which I could find here. Obviously, if this is the distance, then the higher distance is useless to me. So this line indicates any larger value. As you can see, 2 is a larger value before as in the index of 2 is before a smaller value is 1 in this case, is useless. So this 2 is technically useless for me. It should not have been there at the first place. So if this thing, if you look at, so what I'm trying to ideally say here is, so ideally we should maintain only values in some order. What I mean by some order, which means that value if it is small should come before. Any larger value should not come before. What I mean by before in this case, before is if I try to draw my entire values onto a number line, and this number line indicates that as I move on to the right side, this is how the things should look like. This is as I move on to the right side, which means righter index on the right side, lefter index on the left side. So lefter index which I am having should be smaller value. Again, this is kind of inference what above approach or above thing actually told me. And also if I look back, this is what I wanted. Exactly, this is the actual relation which I wanted. In that relation, I just wanted to have the ability to look at the minimum value ASAP. So also I realized that I should have some order of element, in which when I say order, I mean elements are from left to right as an index basis. And also I should be able to get the minimum element ASAP. Some order also to get or apply some operation onto the element, maybe in the front, maybe in the end, or anywhere whatsoever. It gives me an inference of monotonic, because obviously some order should be there in that data structure. This gives me an inference of monotonic data structure. Now, why DEQ specifically? If you see, why DEQ? Because obviously, again, in any ways, if you're ever confused, you can simply go ahead with DEQ, because DEQ gives you all the operations which stack would give you or simple queue will give you. So you have three operations. Either you can use a monotonic DEQ or monotonic stack or monotonic queue. Best is DEQ, because DEQ can perform every operation which stack or queue could do. But in this case, you will see when we do a try run that we would need a DEQ for sure. Let's see what and how. So ultimately we realized the Maqsad that Subarray sum we could achieve by prefix sum for minimum length. Earlier we were actually taking a priority queue. Obviously we thought of we could not use a sliding window, but we were using earlier a priority queue, but now we cannot use. In that scenario we thought of that we will use a DEQ. Now DEQ, if you don't know, has something of this like a queue, but you can push and pull elements from the front. You can push and pull elements from the last. Now things are monotonic. You know the things are monotonic. How will they look like? Is it monotonically increasing? Is it monotonically decreasing? This again, I don't know if you get confused on this or not, but I tend to realize it's monotonic, but I never tend to realize it's increasing or decreasing. So in that case, just look at the statement which I told you previously. I told you previous value should be smaller. If the previous, again when I say previous, I mean index basis. Previous value should be smaller than the next value. So if I am moving left to right, I am telling you that the previous value should be smaller than the next value. So it should be like this pattern. This pattern says that the next value is higher than the previous value in my DEQ. Thus, it is monotonically increasing DEQ which I have to maintain. Again, thinking of monotonic is not a big deal, but thinking of increasing or decreasing is actually a very tricky stuff which people get confused in. So now I realized that I will have a monotonic increasing DEQ. Now, I will maintain this. Let's see by dry run how I will maintain this and take a leverage of this to get my answer. Now, as I told you in the very beginning, for the value of 2, there is nothing in the DEQ. Simply skip that step. But if you go to next element, before that, put that specific index, or I should say the specific value in the DEQ. Now, here in this, I still put a pair of 2, 0, but in the code, you will see I will only put the index, because if again, this is just a simple modification which you can also do. You can also put up in the DQ a pair, that's completely fine. Or you can make this prefix sum array separately, get only the index in the DQ and use that index to go and find the prefix sum value. Both are perfectly fine, will work. Here I am showing in the dry run by corresponding pair, which means value and the corresponding index, but in the code I will show you by corresponding index only I will put in my DEQ. Okay. Now, In the next step, when my j is at 1, you will see my dq so far is filled with 2, 0. I will firstly check the current value is 1. Okay, my dq last value. Aryan, why last? Because I told you this is monotonically increasing. So the minimum value will be at the very last. So I checked, I peaked at the last value, it is 2. Is it more than equal to k? Obviously not. So what I should do? Okay, I cannot increase my answer, but as I go on, I will simply put this specific value of 1 inside my DEQ. How I will put it? I cannot put it in the last. No. If the current element is coming in, it will always come it from the first. Okay, I will put this. But if I put this, which means if 1, 1 will go here, obviously it will it will make my DQ as imbalanced, because obviously I told you this should be increasing. 2, which is a higher value, has come before, which is not the case, which should not have been there. So whenever I am trying to push any new value coming in, I have to remove any value which is higher than or equal to him. Why are you equal to? Because obviously, if it is even equal to, index would have been lesser. I am having an index larger, so I have a lesser distance with the next upcoming element. So thus I remove 2, 0 and then I only put 1, 1. Okay, next let's go on. At the index 2, I will take 4. Obviously, I will have the condition, same condition, that if it is more than equal to, then simply, okay, minimize your answer. But still, you will have to put this corresponding pair, which is 4, 2 inside your DQ. Can I put it directly? Yes, I can put it, because 4 is more than equal to 1. Okay, simply put it here. Okay, 4, 2, 1, 1. I'll simply put it here. Now, okay, go on. I got the value as 7 minus, get the last value 1. Is it more than equal to k? Yes, it is. Simply minimize your answer. How? Current index j, which is 3. Poll the last value. Now, Aryan, why did you poll it? Same reason as why we polled from my heap. If you remember, if I'm using something, I can simply remove it. Right? So if I'm using it, because obviously in the future, this will never be used, because in future, any other index coming in will have a larger distance with this index of MinHeap, or I should say in my DQ. So I simply removed it and the distance will be 2. Again, when this is removed, again, try to repeat the same step by picking from the last. Again, people have their different concepts. Many people put this as first, this as last, but this is how I go about. This is my first, this is my last. Cool. Then I will again do a peak, which is 7 minus 4. Is it more than equal to k? Obviously not. So simply skip and go on forward. When I say skip, which means put your value 7, 3 here and then go on to next value. This is the exact thing what you can do and use a monotonic DQ. If you don't know how to do it, if you want to have some practice problems, go and look at the description below so as to practice on monotonic DQ, monotonic heap, or I should say, sorry, monotonic stack or monotonic DQ. Cool, let's see the code. It's simply simple. It's very easy. Here in this example, I told you, I will maintain a prefix sum as an array. Now, it's not required. You would have simply used a pair as I did above. But again, this is the next variation which you can do. You can simply leverage index to query your prefix sum. So I maintain a DQ, right? Now, my answer, same answer. I go on to every index, same condition as I saw previously. If the prefix sum is more than equal to k, simply go on. This is, okay, if it is not empty, and prefix sum of j, which is the current value, and if I peak the last, if it is more than equal to k, then I should minimize my answer. And when minimizing the answer, make sure to remove that from the last and keep on doing it until you can do it. Okay. And then when this is done, make sure that you will have to put the current pair also inside your heap, or I should say DQ. And when I say put, I mean put it at the front. If I put it at the front, I will have to make sure that anything which is larger than or equal to me should be. If you remembered, when it was 2, 0, I was putting 1, 1 in the front. I removed anything which is larger than or equal to 1 from my DQ, but at the front side. So before putting, again, I did a DQ.add first, the current index. Again, this is nothing but the same pair, the jth pair, which I'm saying. But before doing this step, make sure to remove anything. Here I just checked any value in the first of the DQ, which is more than or even equal to myself. I should remove it from my DQ, because that's obviously unnecessary and will not be required. and thus then I can actually put up my value in the DQ, and thus I will simply remove it and ultimately get the same answer. Because I'm removing and putting every element exactly once, my time is O of n and space will also be O of n because of using a prefix sum array. Cool. I hope you guys got it. Again, even if you would have not used prefix sum array, you would have to use in your DEQ a pair, and the DEQ length would have itself been O of n. Thus, your space would have also been O of n. I hope you guys got it. If yes, then do smash the like button. Do follow us on Twitter. We are very active right now. If you have any questions or queries, it's highly possible to get it clear on Twitter itself. Bye-bye. Take care. Yeah, again, for updates, queries, doubts, personal things, you can just query on, like, again, not LinkedIn, I'll say. Maybe you can query on Discord, Telegram, and Twitter. Bye-bye. Take care.